Good afternoon, everybody. Today we are going to be discussing section 3.3, which is some other common functions besides just the linear and quadratics that we talked about in section 3.2. And we are going to take a look at a couple of graphs of these different types of functions so that we can kind of see what the basics are. And if you are asked to create one of these graphs, at this point what we're going to do is make a table. So I did a couple tables of some of these, and you can pull these notes up or pull these graphs up online and take a look. If you have a graphing calculator, you can also graph these with a graphing calculator and take a look. So a couple different ones are the square root function, and the square root function's base function is y equals the square root of x, or f of x equals the square root of x. And so in my table, I purposely selected perfect squares so that we would get integers, but any number could go in this table except a negative, because that makes it not a function anymore. Then it's in the imaginaries, which is no good. So we stick with 0 and the positives in here. And when you plug in this x, you take the square root to get your y value, and it looks like this. It's a nice little curve here coming up off to the right. The cube function, y equals x cubed, where you take your x coordinate and raise it to the third power. So I chose 5 values this time, -2 to 2, and I cubed all of these values so that we could get this picture, and it's a nice curve up on the right and then coming down on the left. We also have the cube root function, which is y equals the cube root of x. And again, this time I purposely picked perfect cube roots so that we could get nice integers here, but it looks very similar to the cube function. It's just kind of tilted over on its side here. And then we have the absolute value function, which I did discuss in section 3.2, I believe. I drew a quick picture of this just so that you could see it, but there's the table, all of the x values. You take the absolute value of to get the y value, which creates a V shape. So these are just some of the basic graphs, which are also referred to as parent graphs. Oh, I forgot one, the reciprocal function. The reciprocal function is 1 over x, which is a rational function. And if you look at our table, I selected values from -2 to 2, but when you get to 0, you get undefined, because 0 is not a part of the domain of this function. So anytime you have a piece of your function that creates an undefined situation, you will not have it be in your domain. And if it's in the table, you'll see an error or undefined or whatever the case is. If you look at it in the graphing calculator, I think it says error as the y for that value. So there are just a few of the parent graphs. Now we can make a table of values to do our graphs if we want to. I would rather do, since we already graphed quadratics using actual quadratic methods, I'd like to come down to these ones here and make a quick table just to take a look. I'm going to be very purposeful whenever I pick the values for my table, especially in scenarios where you have things that could turn in. Really, this is just, what on earth? My pen is like not working right. There we go. Let's see if we can make this better. Nope, definitely not. All right, we're just going to have to go with it. So for my x value, because I'm dealing with a cube root of x, I'm going to purposely select values that are perfect cubes. So I'm going to start with -8, and then -1, 0, 1, and 8. The reason why I selected these values is because when you take the cube root of these values, you get a nice number. That does not mean that all the values are nice, but if I get to pick what I want, I'm going to pick things that make my life easy. So there's my x values. For f of x, I'm plugging in each one of these values. So cube root -8 and then divided by 2. The cube root of -8 gives me -2. And -2 divided by 2 is -1. And there's a point. And then we keep going in the same manner here. Cube root -1, that doesn't look like a 1, -1 divided by 2. The cube root of -1 is -1 over 2, which is -1/2. The cube root of 0 is 0, and 0 divided by anything is 0, so we're just going to get a 0, 0 there. And then we've got cube root of 1 divided by 2, which is 1/2. Cube root of 8 divided by 2, which is 2/2 or 1. And now these are all of the values that go on my graph. We've got ordered pairs -8, 1, 2, 3, 4, 5, 6, 7, 8, -1. And I don't know if I'll ever be able to connect this correctly. I'll try. We've got -1, -1/2, which is like right there, 0, 0. We've got 1, 1/2, which is right about here, and then 8, 1, which is right here. Oh, so close. Nope, that's 9. 8, right there. All right, and then it's going to look an awful lot like the other cube root. Whoa, that was close. It's just a little bit more condensed, smushed in towards that x-axis. That comes from dividing it by 2, which we're going to discuss at length in the next section over translations. But for now, we're just going to take a look at what these things look like and kind of see what happens. We can do the same thing with the absolute value function. In the absolute value function, it doesn't really matter what you pick to go inside, but I'll pick, oh my gosh, -2, -1, 0, 1, and 2 for my values, and we'll see what happens with the h of x. So again, I'm plugging all of these in. I have -3 times the absolute value of -2. Order of operations says grouping symbol first, and the absolute value is a grouping symbol, so you want to take the absolute value first. And this is -3 times 2, which is -6. And then we have -3 times the absolute value of -1. -3 times 1 is -3. 0 is 0 again. -3 absolute value of 1. That's -3 times 1, which is -3. And -3 absolute value 2 is -3, whoops, that's not even a number. -3 times 2, which is -6. Now, this time, whenever I draw my graph, it's going to look a lot different than the original one. I have points at -2, -6, which is way down here, right there. I have a point at -1, -3, which is right here. 0, 0 still on there. Then I've got +1, -3, which is here, and +2, -6, which is here. When I connect this time, better than this, do better than I did. It still has that V shape, except now the V shape is going the opposite direction. It's like an upside down V, and also it's skinnier. And again, that's going to come from different pieces that we added here. The negative in front makes it flip over, and the 3 makes it skinny. So we'll talk about that again when we talk about the translations in section 3.5. All right, now getting into some actual stuff. Piecewise functions. So piecewise functions are interesting looking in that they are functions that have different, I don't want to say pieces, different functions for different x intervals. So the x's that you can plug into these go from negative infinity to infinity, but they're kind of like chopped up into different groups. Those different groups are the intervals that are allowed to go into each one of the corresponding functions. So it's kind of like a guide for who's allowed in. Like if somebody was standing at the door and checking your ID, are you allowed to go into this function? Well, if you're a part of the interval, then you can. If you are not, then you cannot. So when we're determining what a piecewise function's value is, the first thing we have to do is determine which interval the value belongs to. And that's where this stuff here comes in. These are the intervals of values that are allowed in each one of those functions. Once you determine which interval it belongs to, then you can evaluate that corresponding function. That's these parts, using the given value. It is very important to note that each one of these particular examples will only have one solution because each value only fits into one section of the function. So it's not going to go into all three. It will go into one of the three. Some piecewise functions have 3 parts, some have 8 parts, some have 2. It just depends. But there's going to be more than one function involved in the piecewise function, but only one substitution actually done. So, for example, we have this piecewise function here. So we've got negative 5x minus 8 allowed for values that are less than negative 2. We've got 1/2 x plus 5 for values that are in between negative 2 and 4, including negative 2 and 4. That's why that little equal to part is under there. And then we have the function 10 minus 2x for values that are greater than 4. So each one of these values will fit into one of these particular intervals, and whichever one it works for, you go into that function. You are not going to be substituting anything in to this inequality. You sub here into these ones. This is just the guide. So we're going to start off by finding f of 4. First thing we need to do is determine, where does 4 belong? Who does it belong to? Is it less than negative 2? Is it in between negative 2 and 4, including those values? Or is it greater than 4? Well, because we have this less than or equal to here, this 4 belongs in the middle one. So we're going to use the blue stuff to find our function value. That means I am substituting into this function here. 1/2 times 4 plus 5. And now we evaluate. 1/2 times 4 is 2, plus 5 is 7. This is your function output, which is the solution to this particular problem. This 4 does not go into any of the other places. It fits in this middle category. So we're done. Now we just need to determine where negative 4 falls. So again, we go up to our guides and we say, okay, well, which category is negative 4 in? Is it less than negative 2, in between, or greater than 4? Well, negative 4 is less than negative 2, which means it falls into the green category there. And that means that I'm going to do my substitution into that particular function. So f of negative 4 equals negative 5 times negative 4 minus 8. Negative 5 times negative 4 is positive 20 minus 8 gives me 12. And there's your output. And again, that's your final answer. You get one answer. So that's all you have to do to evaluate piecewise functions. Let's talk about graphing a piecewise function. Goodness, okay. I'm going to end up running out of time, so we're only going to be able to do one, but at least it'll give you an idea. All right, graphing piecewise function. We are going to create tables of values for each of the pieces in the piecewise function. And we are going to base our table of values on the appropriate given intervals. So when we pick our values for our table, we have to make sure that we are in the interval allowed for that piece. We also want to make sure that we use the endpoints of each of the intervals. So the values that are listed, we want to include. This kind of gives you an idea of where each piece will kind of start and end. Unless it's going off to the infinities, then, you know, those are just arrows on that end. So we'll say start / finish depending. If there's only one end value, and again, that's because these things are going to be going off towards the infinities usually, we have to pick at least one other value so that we have an idea of what it looks like. So typically we'll have a couple values, maybe 3 values if we want, to determine what these piecewise functions are doing. So I'm going to look at this example that has 3 different pieces. And again, we are going to highlight so we kind of have an idea here of what each one is, because we're going to have to make some different tables for these things. And I'm going to pick some values for my tables. So I'm going to start with the yellow table. And I'm going to select some x's for this piece of the function, which is x plus 1. Now the endpoint is at -3. So we definitely want -3 in there. And then it says less than or equal to -3. So that means we need numbers that are smaller. So we can kind of, again, just pick whatever we want. And I'll pick -5. That's smaller. We're going to plug these values that we just selected into this particular piece and evaluate. So again, it's x plus 1. -3 plus 1 is -2. -5 plus 1 is -4. And there are 2 points. Now, this interval goes forever in this direction, which means we're not going to have endpoints here. It keeps going with an arrow off in that direction. So when we plot these 2 points, they're kind of just like a guide. Notice that it says less than or equal to, which means that we are allowed to touch the -3 here and keep going off in that direction. So my first point is -3, -2, which is right here. No, right here. No, there. And then we've got -5, 3, 4, 5, -4, 1, 2, 3, 4. And then we're going to connect this with a line segment that keeps going forever off in that direction. And again, make yours nicer than mine. It's just hard for me to write with this pen. So there's the yellow part done. Let's talk about the blue part now. The function for the blue part is -1. And we definitely want to use the -3 and the 4 for our table, because those are the endpoints for this particular piece. Now notice that each one of these points has a less than or equal to associated with it, which just means that we're not allowed to actually touch at these points. So when you have that situation happen where you have less thans here, you can't use a solid point there. You're going to have to use an open point. Only less than or equal to's and greater than or equal to's allow for solid points. Now, when you have a value as your function in a piecewise function or otherwise, this is called a constant function, which means that no matter what you put in, you get out -1. So I could put anything in this interval here, -2, 0, -1, -1.5, whatever the case is, and I would still end up with -1 as my y coordinate. This is constant function. These are the two endpoints, so I'm going to have an open circle, and I'll just kind of connect it straight across whenever I connect my two open circles. So -3, -1, open circle, +4, -1, open circle. And then again, I'm just going to connect it straight because everything in this interval is -1. And now we're done with that part as well. All right. Last part is the green part. And for the green part, I've got x's, well, definitely 4. And then it says we need stuff that's greater than 4, greater than or equal to 4. So since I have to multiply by a half, I'm going to pick an even number, 6. If you pick an odd number, it's fine. You're just going to get a fraction or decimal because my thing is 1/2 x. So since I'm allowed to pick whatever I want, I'm going to pick things that make my life easy. So we plug in 1/2 times 4 is 2. 1/2 times 6 is 3. So we've got 4, 2, solid point, solid, because it's greater than or equal to. So 4, 2, 1, 2, here's my solid point, solid. And then 6, 3, 6, 1, 2, 3. And then again, this one keeps going. It doesn't have a second endpoint, which means it goes off in that direction forever. And there's your piecewise function. Each piece has its own graph to go along with it. Sometimes they are connected to each other, sometimes they aren't. It just depends. But this is a nice example to look at to kind of see what's going on in this thing. And it's 3 pieces, so you get to see 3 different parts. So that's all for section 3.3, which is the last section before we get to the translation stuff. And the translation stuff is going to be what your QEP project is based off of, so it's very important. So I'm probably going to do 1 or 2 videos about it, just so that you guys have it. If you want to see it actually lectured in person and you are available to come to the Hinesville campus, I will be doing this lecture on transformations. Well, we'll probably start it on the 13th and possibly continue it on the 18th of November, which is next Wednesday and the following Monday. So if you can come down, feel free. If not, I'll try to be as thorough as possible in the videos just so that you guys have as much information as possible. So I hope this helps, and keep an eye out for the next video.